In Unit 6, we're going to look at radical expressions and equations, and this is kind of an in-between lesson to help us connect our previous Unit 5 with the upcoming Unit 7. So in Unit 5, we looked at polynomials and how to do operations with them, how to factor polynomials. In the upcoming unit, in Unit 7, we're going to look at how to solve polynomial equations. So Unit 6 is really helping us prepare for solving polynomial equations by talking about radicals and how to simplify radicals and how to solve equations with radicals in them. So in Lesson 1, we're going to really focus on just simplifying some radical expressions and looking at radicals as expressions with rational exponents. And when we say rational exponents, if you remember rational numbers from our first unit are just fractions. So when we say rational exponents, we mean expressions that have fractions as exponents. So before we look at that, we got to talk a little bit about the different types of roots or radicals. So when we're talking about a square root, we always are going to assume that it really means the positive square root. So meaning when I take the square root of a number, so for example, when I take the square root of 49, I'm asking you, what do I have to multiply by itself to get 49? Or what positive number do I have to multiply by itself to get 49? The answer is 7. If I wanted to take the square root of 25, it really means what positive number do you multiply by itself to get 25? Well, the answer is 5. So when you see this definition, or whenever you see the square root symbol, it automatically means the positive square root. And a property here is that what it's really saying is the square root of x is really the positive number that we have to square in order to get x. So whenever you're trying to find the square root of x, it's asking yourself, what number do you have to square to get x? It also works when you look at this property here, that whenever you square root x and then you square it, the square and the square root actually undo each other to get you x. So that's kind of a property that's going to be helpful too. Whenever you're squaring a square root, they undo each other. But really, in this case, what it's trying to tell you is that the square root of x is always, we're going to always say, what positive number do I have to square to get that number underneath the square root symbol? So again, in this example, a positive square root of 64 is 8. So whenever you see this symbol, it's asking you, what positive number do I have to square to get 64? The answer is 8. However, there's also something called the negative square root. Typically, this is not used, but it can happen. But it would have to specify. So if I wanted the negative square root of 64, I would have to ask for the negative square root of 64. I wouldn't write it using just the square root symbol. So the negative square root of 64 is asking you, well, what negative number do you multiply by itself to get 64? And the answer is negative 8. Because really, when you square a number, the negatives are going to cancel, or the negatives are going to become positive. So technically, yes, you could say that the answer to the square root of 64 is negative 8, because negative 8 squared is 64. But it would have to specify that we want the negative. Otherwise, we're always just going to assume that this square root symbol means the positive square root. By definition, we're using that square root symbol as the positive number. So what that means is anytime that you take the square root of a number, you should always be getting a positive answer. This next definition here is just kind of elaborating on the previous one, but we're just applying these different roots to different powers or different numbers. So if I want to find the positive square root, that means what number do you have to square to get the number underneath the square root? So if I wanted to find the cube root, though, notice how the word positive isn't here anymore, because cube roots can be negative. You can take the cube root of a negative number, because if you think about it, it's asking you what number do you have to multiply by itself 3 times to get the number underneath the cube root. And if you multiplied a positive times a positive is a positive, but if you multiply a negative times a negative times a negative, this would end up being here positive times a negative, which ends up being negative. So cube roots can have positive or negative answers. So there's no, like, we're not ignoring anything. Where for even roots, like square roots, fourth roots, we're only ever looking at the positive. We're assuming that the symbol only is asking for the positive answer. So technically, yes, there's two answers for the square root or the fourth root of something, but we're going to be just looking at the positives. That's what the symbol is notating. So fifth root, again, it's an odd root, so you can have positive or negative, and there's only ever one answer. It'll either be positive or negative, not both. And this pattern keeps going on. Notice that whenever we want to notate that we want the cube root, we have an index of 3. That number out in front there is a 3. Fourth root means what number do you multiply by itself 4 times? Fifth root, you put the 5 out in front. What number do you multiply by itself 5 times to get the number underneath the radical? And so on. So you can do this with any number. Down at the bottom here, you have a chart that's just to help you see some of the most commonly used roots that we're going to be looking at, because we're going to talk about simplifying. So you really want to kind of be aware that these are the most common roots and ones that you should expect to see. So just kind of take a look at this chart, use it when you're doing homework, and try to kind of memorize a good chunk of these. It'll just make your life easier. So let's actually look at simplifying. This first answer here, when we want to simplify this cube root of -8, it's asking us, well, what number do we have to multiply by itself 3 times in order to get -8? Well, I know that the answer has to be a negative, because if I want to multiply a number 3 times and get a negative, I have to have a negative to start with. And then the answer for multiplying a number 3 times and getting 8 is going to be 2. So my answer is -2. This one, the square root of -4. For right now, I'm just going to write undefined, because there is no real number that this is going to work for. You can't square any number and get a negative, because remember, squaring a number is always multiplying it by itself twice. So there's no way to multiply the same number by itself twice and get a negative number, because a negative times a negative is positive and a positive times a positive is positive. So undefined, because there is no real number whose square is -4. So it's just not possible to get -4. Now, when you look at this next one, though, this is different, because now this negative is outside of the radical. So I just keep the negative outside, and then I take the square root of 25, which is 5. 5 times 5 gives me 25. When I have an odd root, so now it's the 5th root. So that means I can have a negative. So even roots, you can't have a negative. Odd roots, you can. So when I take the 5th root of -32, it means I have to be multiplying by a negative number, and the answer here is 2. 2 times 2 times 2 times 2 times 2, 5 times, is going to get me 32, and it has to be a negative in order for the final answer to be negative. The 4th root of -81 does not exist, or it's undefined for the real numbers, because there is no real number raised to the 4th power to get -81. So again, because you'd be multiplying something by itself 4 times, there's no way that you would ever get a negative. It's always got to be a positive. When we look at this next example, now we have some variables in here. So first, what I want you to do is I want you to think of this as how many perfect squares do we have in a to the fourth? So a to the fourth is really a squared times a squared. And b to the sixth is really b squared times b squared times b squared. Because whenever you multiply multiply variables, you keep the base and add the exponents. So these two expressions are equivalent. They're equal to each other. But basically, I wanted to split this up because all of these variables are now perfect squares. These are all things that I've squared. So when I actually break this up, when I take the square root of each of these, taking the square root of 25 is going to be 5. Taking the square root of a squared, meaning what do I have to multiply by itself to get a squared? Well, the answer would be a. A times a gives me a squared. The next one, what do I have to multiply by itself to get a squared? Well, the answer is a. A times a gives me a squared. And same for the b's. So each one of those, when I take the square root of it, it's going to get me b. So then your final answer here, well, we have two a's, so a to the second, and we have b 3 times, so b to the third. So there's my final answer. But you might have noticed a shortcut here. So instead of going through this whole process that I just went through, basically you just take the square root of the number, but if you look at the exponents, really what I did with the exponents is I divided the exponents by 2 because I was taking the square root. I was asking myself, what do I have to multiply by itself twice in order to get a to the fourth and b to the sixth? So I just essentially just divided those exponents by 2. So I'm just going to write that down as a rule. We're going to just divide exponents by whatever the root is. So square root divided by 2, cube root divide exponents by 3. So let's look at another example. So here I'm taking the cube root. So all I need to do is divide each of the exponents by 3. So x to the 6th is going to become x to the 2nd. And y to the 12th, when you divide that by 3, is going to become y to the 4th. So for this one, I'm taking the cube root of x to the 6th, y to the 12th. So you're going to divide each of the exponents by 3. So x to the 6th is going to become x to the 2nd. Y to the 12th, well, 12 divided by 3 is 4. So that's it. That's much shorter than doing the whole process that I did in example 7. Now you could do that process where instead of writing it out, everything written out as a perfect square, you would write everything out as a perfect cube, and you would find out that you had to do that twice for x and 4 times for y. And then this last example, if I want to take the fourth root, well, the numbers, this is what you have to be careful of. When you're taking the fourth root of 81, it's not dividing 81 by 4. It's asking yourself, what do I have to multiply by itself 4 times to get 81? So just make sure you're careful. Exponents and the coefficients are treated differently. The numbers always follow the root, and then the exponents have a different rule. So for this one, what number do I have to multiply by itself 4 times to get 81? Well, the answer is 3. And then for the exponents, so you keep the r, you divide 8 divided by 4, so we get 2. And then s, 20 divided by 4, is going to give me 5. So there's your answer. So now let's look at some other examples with talking about those rational exponents. So whenever you have a rational exponent, meaning a fraction, the rule is listed here as 1 over n. So anything raised to a fraction exponent is the same thing as saying that n is really the root. So I remember it as the roots are always in the denominator. Think about like the roots in a tree. They're at the bottom, they're in the ground, so they're the lower thing. So the roots are always in the denominator of the fraction. That's always going to be the number that goes out in front. And then the powers are always going to be up top. So powers are always higher, so those are up top. So when we want to take these examples and rewrite them as a root, anytime you have something in the denominator, that's going to go out in front, and then you're just going to keep everything else. So since these all are to the power on top, or in the numerator is 1, I'm not going to worry about writing the 1 for right now. So then I'm taking the cube root of 8, which is 2. So 36 raised to the 1/2. Well, really, this is a 2 out in front. The root is 2. However, for shorthand, we don't ever use this, like the 2 out in front of the square root. We always just use no number out in front, since the square root is the most common one. So you don't have to write the 2 out in front. If you wrote the 2 out in front, it's not wrong, but we just avoid it because it's just for short, to be shorter on it. So then you take the square root of 36, we get 6. So then the next one, we have negative 25 to the 1/2. The negative is not included with the 25. So this is really negative, and then the root is 25 to the 1/2, so the square root. So this becomes just negative 5. You just keep the negative out in front. Now this one, notice the difference between these two examples. This one, the entire thing is being raised to the 1/2. So this means that the entire thing is underneath the square root, or underneath the radical. So for this one, we just have to say there's no real number, or again, undefined, because remember, you can't take the square root of a negative number. And you might be thinking, well, yes, these are imaginary numbers, but we're not there yet. We're just going to say for right now that these are no real numbers. The next example here, we have a fraction. So again, it's the square root of all of these pieces. So that entire fraction is being raised to the 1/2. Whenever you're taking the square root of a fraction, it's really just the square root of 4 over the square root of 9. It's just square root each piece. So square root the top, you get 2. Square root the bottom, you get 3. So now let's look at some other more complex expressions. So first thing we're going to do is we're going to write each radical with a rational exponent, meaning as a fraction. And up top here, I just added in the properties of exponents. So hopefully you remember these, but if not, take a look, refresh your memory. I kind of talked about this one here, where whenever you are multiplying like bases, you add the exponents. Whenever you're raising to a power, you just multiply the exponents. If you have two things raised to the same power that are being multiplied, you can raise each individual one to the power. Any negative exponents are going to go to the bottom. It's going to be the reciprocal. Any fractions raised to a power, which we kind of just saw with that 4/9 raised to the 1/2, you just raise each individual piece to that power, or square root each individual piece. Whenever you divide, we saw this in the previous unit, whenever you divide exponents or divide bases, you subtract the exponents. So let's look at some examples where we're going to use those. So the first thing I'm going to do, since this is talking about the cube root, so instead of being given the fraction, I'm going to take something that's already written with a radical, and I'm going to turn it into an expression with the fraction as an exponent so that I can use those exponent rules. So really, this is going to be x to the 6 times y to the 12, all raised to the 1/3. And then I can apply that third property up there, where I can take each individual piece and raise each individual piece now to the 1/3, since the operation between these is multiplication. And then from there, I'm going to apply property number 2, where I can rewrite these as 6 times 1/3. So 6 times 1/3 is really 6 over 3, because remember, when you multiply fractions, multiply across the top, multiply across the bottom. And then y is really going to be 12 over 1 times 1/3, which is 12 over 3. And then you just simplify these. So 6 divided by 3 is 2. 12 divided by 3 is 4. So this is just a different way of simplifying. Now remember, in that in one of the previous examples, when we saw this, we said, well, that just means divide each of the exponents by whatever the root is. So we could have just taken that and said, well, x is going to become 6 divided by 3, which is 2, and y will become 12 divided by 3, which is 4. So that's much shorter. Right now we're just practicing using those exponent properties. Sometimes using the exponent properties in fractional exponents will be easier. Other times this way will be much shorter. So you have to know both because they'll be used for different cases. So example 16. Again, you can apply it how we did in those previous problems where we just divided the exponents and we actually took the fourth root of the number. Or you can take this and you can rewrite it using a fractional exponent. So we have everything is raised to the 1/4. So this means I can split this up because everything is being multiplied. So it's every single piece is being multiplied to the 1/4, or being raised to the 1/4. So 81 raised to the 1/4 is really asking yourself, what do you have to multiply by itself 4 times to get 81? The answer is 3. Here I'm doing 8 over 1 times 1/4, which is really r to the 8 over 4, because you multiply across the top. And then this other one is going to be 20 over 4. So you end up with 3r to the second, s to the fifth. So you are just dividing these exponents by 4, which is really what we came up with previously when we said, oh, just divide the exponents by whatever the root is. And this is kind of like why it all works out. But again, you can remember the shortcut, but in this case, we're just using those properties. So let's look at a couple more examples. So on this page, we're looking at some more properties, which I kind of already talked about. Whenever you have the roots, so this is saying that a raised to the m over n. Let me just start it. So a raised to the m over n. N is the root, and m is the power. So it's easy to remember because the roots are always in the bottom. Power, if you think about someone who has power, they're always on top. So we have the numerators are the powers, the denominators are the roots. So when I rewrite this, I can say that a to the m over n is really like saying the nth root of a raised to the m power. So a is raised to a power. This is also the same thing as saying the nth root of a where the entire expression is raised to m. So these are all equivalent. If you look up here, here's some other equivalent expressions that you can take that m outside of the expression. So I could also say, so let me just kind of rewrite what they have up there. So m over n, they're saying, well, this is the nth root of a, then raised to the m power. Or you could say a raised to the m power and the nth root of that. So these are really all equal. They're all equivalent, so you just kind of have to be aware of the differences and that you could see them and that they all end up being the same. Keep in mind these two examples here. I have my fractional rules that apply here, my exponent rules. You're multiplying, so that's why you can rewrite these like this, where you separate the m and the 1n, 1 over n. Because of your exponent rules, you just multiply your fractions whenever you're raising to a power. So let's look at this example. If I wanted to simplify 8 to the 2/3, what this really means is 8 to the 1/3 squared. So what this means is 8 to the 1/3 is really the cube root of 8. So what do I have to multiply by itself 3 times? Well, the answer is 2 in order to get 8. So then you take 2 and you square it, so you get 4. So that's really what that means. Same with this example here. This says 25 So the 1/2 is the root, and it's raised to the third power. So if I want to take 25 to the 1/2, that's asking me the square root of 25. So that's 5, and then raise it to the third power, you get 125. So negative, or 9 raised to the negative 3 over 2. So again, think of it as you're taking the square root of 9, or 9 raised to the 1/2, you'd be left with a negative 3. So take the square root of 9, you get 3. Raise that to the negative third means that you would rewrite it as 3 to the third in the denominator to make that positive, and then this becomes 1 over whatever 3 to the third is, which is 27. And then this last example, so this example here, what I would do is first rewrite it as 27 over 8 raised to the 1/3, which will then be raised to the negative fourths, negative 4 power. So when I take the cubed root, so I'm going to start there. If I take the cube root of 27, I get 3. Take the cube root of 8, you get 2. And then raise this to the negative fourth, which means since this is a fraction, if I do 1 over this whole thing, it really just means you flip them. So this means 2 over 3 really raised to the fourth, which then means 2 to the fourth over 3 to the fourth, which is 16 over 81. So this stage here, this step that I did, this step is like me saying 1 over 3/2 to the fourth, just like what I did in that previous problem where I took whatever I had raised to the negative, I put it in the denominator, so then that makes the exponent positive. That's our exponent rule. But because this is 1 over this fraction, this is equivalent to saying, if you remember dividing fractions, keep, change, flip. So I keep, I change, and then I flip the bottom. So I end up with 2/3 to the fourth. So remember when you divide fractions, keep, so you keep, you change, and then to multiplication, and then you flip the fraction. So that's how I did this shortcut. So I just knew that I could just flip it and they would be equivalent. Alright, a couple more and then we're done. So here's just another set of examples that have fractions, just more than one term. So we're using those exponent properties. So here we need to add these because we are multiplying these variables and they have the same base. So we're going to keep the base. So I'm just going to kind of write out the rule here. So keep the base, add the exponents. So when I do this, I keep the base and I add 1/3 plus 5 over 6. And if you remember, when you add fractions, you got to get a common denominator. So off to the side, I'm going to do the addition. So 1/3 plus 5 over 6 is it's going to end up being, our common denominator is going to be 6. So I'm going to rewrite these with a denominator of 6. And in order to change this first one into a denominator of 6, I have to multiply everything by 2. So I have 1 times 2 is 2. And then the other one I can just keep as 5 over 6. When you add fractions, you keep the denominator and add the numerator, so we get 7. So that means over here, my expression is going to be x raised to the 7 over 6. This next expression, because we're raising to a power, the rule is you keep the base. Keep the base and multiply the exponents. So we've seen examples like this. So you're going to keep the base, you multiply the exponents. When you multiply x fractions, you multiply across the tops. So 2 times 3, you get 6. Multiply across the bottom, 3 times 4, you get 12. And then you can reduce this fraction up top. So 6 over 12, 6 goes into both the numerator and the denominator, so divide each thing by 6, you get 1/2. So this is really the square root of y. Here we are dividing, so we keep the base, and we're going to subtract the exponents. So you're going to have z to the 1/3 minus the 1/4. So off to the side here, let me do that. So 1/3 minus 1 to the 4th, or 1/4. My common denominator for both of these is going to be 12, because 3 and 4 both go into 12. So now you have to ask yourself, well, what do you have to multiply by 3 to get 12, which is 4. So you multiply both by 4. And then for the second fraction, what do you have to multiply 4 by to get 12, which is 3. So you put 3 up top, 3 times 1. And then keep the denominator, subtract the exponent. So 4 minus 3 gives me 1. So over here, my answer is z to the 1/12. And then this set of examples here. So now we have some other properties. So I have, first thing I want to do is, since this is a fraction, all raised to the 6th power, I'm going to rewrite everything as individual pieces raised to the 6th. So b to the 1/2 raised to the 6th power. You can't combine anything in parentheses, just so you know, because these are different bases. So I can't do anything with the numerator and the denominator. All I can do is raise each of them to the 6th power. So when I raise these to the 6th power, I'm going to keep the base and multiply the exponents. So I'm going to have a to the -2nd, because -1/3 times 6 is like 6 over 1. So -6 on top divided by 3, which is going to be -2. And then at the bottom here, I'm going to have b to the 3rd, because 1/2 times 6 over 1 is really 6 over 2, so b to the 3rd. And then the last thing I can do is, because I have a negative exponent up here, I'm going to just move that a squared to the bottom, and it's actually going to go with b to the 3rd, because b to the 3rd is going to stay there. All right, last and final example here. So I have an expression here up top that has everything in parentheses being raised to the 4th. So the first thing I'm going to do is I'm going to take each individual piece and raise it to the 4th. And then I'm just going to copy everything in the denominator. So now I'm going to simplify the top. So I have x to the -12 and y to the 2nd. When you multiply those exponents over x to the 10, y to the 3/2. And now you have a couple like bases. So I have these that are like bases. So I'm going to keep the x and I'm going to subtract. So -12 minus 10. And then y, it's going to be 2 minus 3 over 2. So let me do that fraction subtraction here. So 2 minus 3/2 is going to be, my denominator has to be 2, since I have 2. So keep in mind that any whole numbers are always over 1, so you'd have to multiply everything by 2 in order to get that denominator of 2. So you'd have 4 minus 3, so we get 1 over 2. So that means over here I'm going to have x to the -22, y to the 1/2. And the last thing I should do is, since this x is raised to a negative exponent, is going to be to move it to the denominator. So I'm going to keep the y to the 1/2 up top, and the x to the 22 is going to go down in the bottom. So you've done a lot with fractional exponents. You've seen how you can rewrite them as roots. You've seen how to simplify them, and you've done some exponent properties with them. So it's a lot in this video, but make sure that you really spend some time knowing those exponent rules and practicing simplifying because it's going to really come up in the next lessons.